This is Professor Thompson, and I'm going to do some more examples of curve sketching. And the example I'm going to do is y equals e to the x over x. So in your book you did x e to the x in the examples, and so now I'm going to divide by x instead. And I'm going to follow the steps in the book. So first I care about the domain, and the only problem here is that if x is 0, then I'm dividing by 0. So this is minus infinity to 0, union 0 to infinity. Then I want to know about the x and y-intercepts. And if x is 0, we already threw that out. That's not a situation that happens. If y is 0, that means the numerator, e to the x, that has to be 0. But we already know that e to the x is never 0. It's in fact always positive. So there aren't any intercepts. The next step is symmetry. But we definitely don't have any periodic symmetry, and if I make x minus x, then I have e to the minus x over minus x. That's minus e to the minus x over x, which is not the negative of the original, nor is it the same, so I don't have any odd or even symmetry, so I have no symmetry. Now, for asymptotes, we'll do that on the next slide, because we have a lot to think about. So first let's talk about vertical asymptotes. The definition there is that the limit as x goes to some point, if that is plus or minus infinity from either side, that's what we call vertical asymptote. So that means that the function's not defined there, so the only possible point is 0. So we take the limit as x goes to 0 of e to the x over x. Well, the top becomes 1 and the bottom becomes 0. Which means that it's an asymptote there when you have something non-zero divided by 0. So x equals 0 is a vertical asymptote. Now we don't know which infinity it's going to on each side, but we're not worried about that just yet. We're going to find that out when we do our intervals with the second derivative. Now horizontal asymptotes, those are the limits at infinity. So if I take x goes to infinity, I get e to the x over x, which I get infinity over infinity, so that's indeterminate, which means I'll use L'Hopital's rule. So this is the same limit as e to the x, which is its own derivative, over 1. Now the limit there is infinity. And if I take the limit as x goes to minus infinity, well, e to the x goes to 0 in that case, and you're still dividing by very, very large numbers, just negative, so it's 0 in that case. So I don't have a horizontal asymptote on the right, but I do on the left. So y equals 0 is the horizontal asymptote on the left. So now I've got all that data, and now what I need to do is find increasing, decreasing intervals and all that. So I start with the function, and I take the derivative. What I'm going to do here is I'm going to take the derivative using the quotient rule, so that I keep it a fraction. So this is low d high minus high d low times 1 all over low squared. And now I want to figure out when that's 0 undefined, so I want to factor it. So I'll factor out e to the x, and I get x minus 1. Well, the critical points, or critical values, that's, let me say critical values. That's when the bottom or the top is 0. The bottom is 0 when x is 0. And when x is 1, the top is 0. But then e to the x, that's never 0. So those are my critical values. So I make a sign chart, and I go from minus infinity to 0, 0 to 1, and 1 to infinity. So my test values, I'll use minus 1, a half, and 2. And I have 3 factors here, e to the x, x minus 1, and x squared. And that'll tell me the sign of f prime, and that'll tell me if f is increasing or decreasing. This is a pretty easy sign chart because e to the x is always positive, and so is x squared, as long as I'm not plugging in 0, which I'm not. So if I use minus 1, minus 1 minus 1 is negative, so the whole thing is negative. That's decreasing. And then I have a vertical asymptote at 0. And after that, when I use a half minus 1 is negative, so I'm still decreasing. And then if I use 2, 2 minus 1 is positive. So now I'm increasing. So that means when x is 1, I have a local min, because I decrease then I increase. So let me write at the top here. I have a local min at when x is 1, and that makes y e. If I plug back into the function, e to the 1 is e divided by x equals 1. So e to the 1 divided by 1. Remember, e is just a number. It's 2.78, something after that. Almost 3. So I've got my local min, no local maxes. Now I want to do my second derivative information. So that was really e and f. So now, well, let's look at our second derivative again, which was x e to the x minus e to the x over x squared. So I need to take the second, that was the first derivative, so I need to take the second derivative. And it's kind of a bust either way if I had factored the top. But let's see what we get here. So this is low d high. So the derivative of the high is going to require the product rule. So that's going to be x e to the x plus e to the x for the product rule minus the derivative of e to the x, which is e to the x. So that's where that's coming from. And then this is minus high d low, which is 2x, all over low squared, which is x to the 4th. And away we go. So I need to simplify that numerator. Well, the e to the x's here cancel, fortunately. So I have x cubed e to the x minus 2x squared e to the x plus 2x e to the x all over x to the 4th. So I guess I can cancel an x out of everything because I see it in every factor in the numerator. So the way that works is I'll factor x e to the x from the top, and that gives me x squared minus 2x plus 2 x to the 4th. Now I can cancel that guy with one of those and make that a 3. So if e to the x, and then I have this quadratic that doesn't factor, and let's just look at the determinant of the quadratic formula for this guy right here. So if I take b squared, which is 4, minus 4 times 1 times 2, that's going to be negative, and I'm going to put that in the square root for the quadratic formula. That means that the roots, the two zeros of this, are complex numbers. They're not real numbers. So that means that there is no real zero in that quadratic, and e to the x is never 0, so the top can't be 0. So all that's to say that x equals 0 is the only CV, only critical value here. So now I need to make a sign chart. So let's go ahead and do that. So it just goes from minus infinity to 0, and then 0 to infinity. And the factors I have here are e to the x, x squared minus 2x plus 2, which doesn't factor, and x cubed. All those together will tell me f double prime sign, and that'll tell me if f is concave up or concave down. So I'll use minus 1 and 1. I forgot to put room for my test values. But I'll put over here minus 1 and 1, or what I'm going to use. Well, e is always positive. If I plug in minus 1 here, I get 1 plus 2, which is positive, but then x cubed would be negative. So I'm concave down. And then when I use 1, I get 1 minus 2 plus 2, which is positive, and then x cubed is positive. So now it's concave up. However, I don't get an inflection point because remember 0 was the asymptote. So now I have all the info that I need And now I'm going to try to sketch. So let's start with the axis and the fact that the y-axis is a vertical asymptote and the x-axis is a horizontal asymptote on the left. And we found a minimum when x was 1 and y was e. So almost 3 here. So maybe right there. So that was our only real interesting point. And so let's just work to the right. On the right we said concave up. And we said before 1 we're decreasing and then we're increasing afterwards. So we should get something like this. Except I should go down all the way to that point there. And then to the left, we said that we were concave down, and we were always decreasing. But remember, 0 is the asymptote. And so, remember, e to the x is never positive, never negative, but we're dividing by negative values of x, so we should be under the axis. So we should get something like this. Because we have the asymptote on the left, and then we have the vertical asymptote on the right. So that thing is concave down, it's bending downward, and it's decreasing. And it's approaching both asymptotes. So the graph should look something like this.